number 6, we have a chi-squared problem with a little bit of probability. So we have that a company that owns many restaurants wants to determine if there are differences in the quality of food. Okay? Differences in the quality of food cooked for 3 different meals: breakfast, lunch, and dinner. The quality assurance team randomly selects 500 items of food to inspect, and the quality of this food is classified as perfect, satisfactory, or poor. The data is summarized in the following table. So just so that we're all on the same page, for example, there were 101 perfect breakfasts. There were 81 satisfactory lunches. There were 114 dinners, okay? And there were 204 perfect meals, okay? That is how you read this table. And keep in mind that these edges over here are totals, okay? These are totals. All right. So an item of food, for some reason, is chosen at random from these 500. And for part A, you need to find the probability that its quality is not perfect. Ah, look at this. Given that it is from breakfast. That right there is huge, okay? So there's 2 main things I have to explain here, okay? The first one is how this exercise would be if this was not written here at all. So if this was not written here at all, you're just trying to find the probability that its quality is not perfect. And so the item which has a quality that is not perfect is going to be, for example, all of these and all of these. So in other words, for the probability that its quality is not perfect, you would be saying, okay, so my total is 500 because you are picking from these 500, right? So you pick from those 500. So that's going to be where you're picking from. So it's going to be the number at the bottom, your total, right? And up top, you're going to be saying, okay, so those that are not perfect are the satisfactory, 274, plus the poor ones. So for not perfect, it's either satisfactory or poor, okay? So you go ahead and do that, and you would be doing 296 divided by 500, okay? So that is how you would solve it if this exercise would say, find the probability that its quality is simply not perfect, okay? Here's the thing. The exercise puts in the word given, okay? The word given, I need you to understand that the word given, okay, has to do with conditional probability. And so the main word that gets thrown at you is either given, or if you hear something like if. Okay? Now what's happening here? Notice in my original approach, I put the total on the bottom, right? And this is usually how probability goes. You put the total from the bottom where you're picking from, and up top, you put like your plausible cases. Plausible cases up top. See? Yeah, so up top, you put the plausible cases. Down on the bottom, you put your total. So, ladies and gentlemen, given that it is from breakfast, how does this change my total? And that's the other thing that I gave you the answer pretty much, but the main idea of conditional probability is that this, and write it down, changes your total. That's all that happens, okay? If initially, for the first version that I showed you, you're picking from any of these. Well, now what's happening is that given that it is from breakfast, you are only picking from breakfast. So suddenly, kapow, kapow, you don't care about this. Now what you're calculating, the only set of data that you actually care about is this rectangle that I'm putting now in pink. This is your new total. So that's the first thing I'm going to mention. That is your new total because you're finding the probability its quality is not perfect given that it is from breakfast. So given that it's from breakfast, you only care about breakfast. You don't care about lunch or dinner anymore. Bada bam, bada boom. So your new total is going to be, well, all of those that did breakfast, which, look at that. Conveniently, there's a total column right here. So on the one hand, your new total is 232. Okay? And up top, it's still going to be for plausible cases. So plausible cases is, okay, those that within breakfast are not perfect. And those that are within breakfast that are not perfect are this 124 and this 7 right here. So you go ahead and do some quick maths. You end up with 131, if I'm not mistaken, divided by 232. Let me double check that. It looks fine to me. See? So the big idea I need you to understand is that conditional probability, which comes through given or if, changes your total. There is a formula from the formula booklet for this, okay? And if I were to get very fancy, I would just tell you, oh yeah, for a given probability, it's like this. So that stick right there, it means given. Okay, so A given B is going to be P probability, sorry, of A and B. Remember that this right there is for and, okay? Divided by probability of B. So you can do it very rigorously. We could have applied this formula in this case up here and it would have worked out. But because we had the table here, I think it's very visually appealing to understand, yo, it changes your total. So once we're talking about just breakfast, because it is given that it is from breakfast, you don't care about lunch, you don't care about dinner, your table gets a lot smaller, and so does your total. That is the biggest idea I can share with you. Do not forget, the whole point of conditional probability is that it changes your total. That's why people use it in the first place. Be very aware of that. So there's my new calculation. So it's 131 divided by 232. I check over here. Whoops, that is a little bit of a spoiler, but we'll get to that in a second. 131 divided by 232. There it is, 0.56. We check the answer key, and it's right there. See, 131 divided by 232, 0.565. So for part A, make sure you leave your answer in either significant figures or as fraction, decimal, etc. I'm just going to leave it like this right here. Okay, so that would be for part A. All right, and now for the next part, it gets a little bit more juicy. So on the one hand, we have, or they tell us that a chi-squared test. See, this fancy x with the squared is just a chi-squared. Okay, don't get lost in the sauce with that. It's a chi-squared test. So a chi-squared test at the 5% significance level is carried out to determine if there's a significant evidence of a difference in the quality of the food cooked for the 3 meals, which is exactly what the company was trying to find out earlier, right? Are there differences in the quality of the food? Is the breakfast always perfect and is dinner always poor? We have to balance that out. Like that's what the company wants to figure out. See? If basically there's a big difference between the type of meal and the quality that it gets. So they also tell us that the critical value for this test is 9.488, and they give us the 2 hypotheses. See, the first thing I'm going to mention is that H0 will be your null, okay, and that H1 will be your alternative. So there's too many observations I can kind of try to do here, right? I know that a lot of times in the IB, you need to actually write the H0. You have to actually write the H1. And so a tip that I think a lot of people appreciate is that sometimes it works perfectly well that H1 is going to have the word not inside of it. I mean, if you see the difference between these 2 hypotheses, it's really just the word not. I mean, literally, everything else is word for word. The quality of the food and the type of meal are, and boom, if you're H1, you're putting the word not. If you're H0, you're not putting the word not. All right. So that's just a quick tip on how to get the hypotheses like correct. And notice for H0, it's that they are, quality of food and type of meal are independent. And so that's a little bit like there is no difference. See, well, for H1, if they're not independent, that means there is a difference. Okay? So notice that. Null is usually like no difference. So because they're independent, it's no difference. But if they're not independent, then there is a difference. Okay? And how do you express that? Well, H1 has to have the word not. H0 doesn't. So those are the two main tips I can give you for creating hypotheses, because I know that happens sometimes. Now let's get into the action. So for part B, you need to find the chi-squared statistic. Now this is actually fairly simple. We just need to have really clear what my tools actually are. Okay? So I'm not going to show you the tools and have you memorize them. I'd rather explain the thought process that I want you to go through. Right? So the day of the test, you're going to encounter this problem, right? And then you're going to read all this stuff about significance level, critical value, etc. Maybe you don't remember it too well, but it's going to slowly come back to you. And one of the things that I need to have come back to you are the tools you have here, okay? So how do you identify the tools? Well, you need to find a chi-squared statistic. So what are your chi-squared tools? You have two main tools, okay? And you're not going to remember which ones they are because no one remembers them by memory. But you do know that, yo, this is a test. So you're going to open up your graphing calculator. You're going to go ahead and press stat and go to the column of tests. And this is where you're going to look for your chi-squared tools, okay? So notice, I'm not saying that you read this exercise and you know immediately what to do, but you should be able to read this exercise, look at the word test, which is a big buzzword here, and say, ah yeah, so I'm testing something. I know there's a testing area somewhere in my calculator, find it, and look for your chi-squared. I assure you, you're going to find a bunch of stuff, see, that you don't need, probably have never used, and maybe never will use, but eventually you're going to find these two chi-squareds, see? So your chi-squared tools, we're going to call it just chi-squared, okay? And you also have chi-squared GOF, okay? I'm pretty sure GOF was for goodness of fit or something like that, but we're going to leave it even more intuitively than that, see? So you have the chi-squared one, and then you have the chi-squared GOF. So what's the difference here? What is going on, right? Well, again, you're not going to remember because no one has magical memory. So you're going to press one by one and see what they ask for. So depending on what they ask for, you're going to see, this is when I use this. That is when I use that. So if I press the chi-squared one, it asks for these big letters. If it asks for the big letters, then we're actually talking about a matrix. If you haven't seen this before, do not worry, I got you. So the normal one, the chi-squared by itself, is going to be a matrix, which for us, puny human individuals, we're going to remember it as a table. So whenever you have a table, you're going to be using the matrix, okay? On the other hand, if we go ahead and check the other test, which is chi-squared GOF, it asks for lists. And so this one's more apparent, right? It's asking for a list. So that's like L1, L2. The table for the matrix is literally something that looks like this. A encapsulated by a bracket that looks like that. B that looks like a bracket like this, okay? So right now we just established, okay, the two main tools are chi-squared and chi-squared GOF. Chi-squared GOF is asking for lists. Here I don't have a list. Here I have a table. I mean, and you might be thinking, oh, but I can put 3 lists. You can only put 2. L1, L2. Okay? So that's the first thing I'm gonna establish. So here in this exercise, I will not be using GOF because I don't have lists. I have a matrix. So go ahead and put it into your matrix, right? Now, where the heck is the matrix? It's right below math, right on top of this button here, see? There's gonna be second, that button here, and you hit matrix. And well, I did do it earlier, but I'm going to show you again. Basically, you just have to edit the first one, right? You have to edit A. Now, you probably have something that looks like this. Whoops. you probably have something that looks like that. Okay, you probably have like a matrix that is smaller or maybe bigger. You need it to be aligned with what you have on the exercise. Yeah, and there's something very important that I need to establish. Okay, although for calculating the chi-squared statistic, the total columns are super essential, your calculator does it for you. So actually what you need to plug in is only this right here. Do not plug in the total columns. It is not your job to go over that. So plug this in and only this in to your matrix on A. And so that matrix on A that I just put in pink, well, it's 3 rows and it's also 3 columns. So clearly it is a 3 by 3. So that's the first thing I'm going to do. Up top, I'm going to change it to a 3 by 3. And then I'm going to put in all the values. So the 101, and put it in order as well. Important. 1, 2, 4, 7. You basically want a table that looks exactly the same like the one in your exercise. See? Yeah. So there, I plugged in just matrix A. See? Now, if I go back to the stat and the test and the chi-squared, notice for my observed, I have matrix A. For my expected, I have matrix B. And you might already be thinking, don't I have to create an expected matrix for B? And I say, nuh-uh, your calculator is your best friend. And best friends sometimes do your homework. Just kidding, don't do that. When the calculator, when you put the observed matrix on A, it automatically calculates your expected matrix on B. Trust me on this, okay? You do not have to get into the details of calculating the expected values in a different matrix. All you have to do, okay, is plug in the observed and the expected will be calculated for you. So go ahead and press calculate. We don't care about drawing this time or ever probably. Just go ahead and press calculate, see? And there you go. You get 3 things, see? You get the chi-squared statistic, which there's your answer for part B. So for part B, the chi-squared statistic is 11.021. Might as well put a couple more numbers. 23361. 23361. So there is my chi-squared statistic. How do you show your process? You will literally have to like, I mean, if you show this, like visually, if you show this, you're gonna get full credit. See? So somewhere down here, writing your answer, you have to be very clear that this is the table that you put into your calculator and you put it into a matrix. How do they know that it's a matrix? Because you're writing the big letter A between these brackets like this. That is the language for matrices. Okay. So that is how you get the method point if there were to be one. For these exercises, usually there isn't a method point, so it doesn't really matter, but just so you know, okay? Yeah. That is for part B, all right? And the last part, which is actually when I'm going to start talking about what chi-squared even does in the first place, notice that everything else was just procedure, like what you have to know by heart, okay? Now I'm going to explain your procedure, maybe make it a little bit more friendly, maybe help us understand, okay, this is my chi-squared. What the heck do I do with it? See? So for part C, we need to state with justification the conclusion for this test. So this is going to be the more hardcore statistic mathematic part of the video. So buckle up and good luck. Yeah. Here's the main idea. So a chi-squared, its purpose. Pass the butter. Its purpose is to, I'm going to say compare. Yeah, so compare the differences between observed and expected values. Okay? So in the chi-squared test, you compare the differences between observed and expected values. If the difference is too big, then maybe H0 is wrong, right? Because let us remember that H0 usually has to do with like there is no difference, things are independent, everything's okay. H1 is usually like there's a problem, there's a difference, there is a statistical sort of like issue going on, right? So if the difference is too big, then maybe H0 is wrong, okay? And so just to hone in on that a little bit more, right? This company picked 500 different meals at random between breakfast, lunch, and dinner. They evaluated if it was perfect, satisfactory, or poor, and these are the numbers that came out. See? Now, just like throwing a dice, and you can throw a dice and get a 6 10 times in a row, see? You have to evaluate, okay, how likely is that? See? Because if the probability of that is extremely, extremely low, and some magician does it 5 times in a row, 5 times in a row, they get a 6 10 times in a row, well, that's kind of crazy. It's probably a loaded dice. You can start concluding stuff like that, see? Because it is a little too far out, and here's the main idea, from what you expect. And so the chi-square statistic, think about it this way, okay? The bigger the chi-squared statistic, the bigger the dispersion, maybe the difference. The bigger the difference between between observed and expected values. So maybe this is a bigger idea you can write down. The bigger the chi-square statistic, the bigger the difference between observed and expected values. Now the obvious question here is that at some point it gets too big, right? But how do you evaluate if it's too big or not? So for evaluating if it's too big or not, you would basically say, if the chi-squared is bigger than critical value, then it's too big, okay? That's basically it. If the chi-squared is bigger than your critical value, then it is too big. The other thing you do is that if the p-value, which we got over here in the calculator, right? If that p-value that came out here, right, is less than your significance level, right, then it's too unlikely. Okay, so these are two sort of things. Whoa, what the heck just happened? That's crazy. All right, this just glitched out really hard. Wow, that's new. All right, cool. Wow. Anyways, so there's two ways to conclude, okay? Two ways to conclude. If your chi-squared is bigger than your critical value, then it's too big. Now, what's too big? Then the difference between observed and expected is too big. The other way that you can conclude is using the probabilities, right? Because these values there are not probabilities. The p-value and the significance level is. So if the p-value is less than the significance level, which is a probability of 5%, then, god dang, then it is too unlikely. So you either say, okay, these values are way too far from my expected, or what I'm observing is far too unlikely, okay? So essentially, for concluding, you have your chi-squared, which we said was 11. Let's leave it at 11.0, okay? And you also have your critical value. So critical value, they told us, was 9.488, okay? So on the one hand, you can say that, okay, the chi-squared is clearly bigger than the critical value. And this, by the way, just so you know, is your justification. So if chi-squared is bigger than critical value, then the difference between observed and expected is too big. And so if the difference between observed and expected is too big, then the quality of food and type of meal are independent. Then you reject HO, right? You would have to reject HO. Just to check over here. Exactly. You reject HO. Okay? So that is one way you conclude. If the chi-squared is bigger than critical value, you reject HO. The other way you can sort of memorize it if you want is the alternative, which is if chi-squared is less than critical value, then you fail to reject. You can also think about it as you accept HO. See? In this case, we have the scenario that I'm putting now in red, because you only have to compare 11.0 being bigger than 9.44488. See? So clearly you reject HO. The other way you can conclude is using the p-value and the significance level. So make sure you're associating the right things with the right things. P-value with significance level, chi-squared with critical value. Okay? The other way you can say, the other thing you can say is, okay, so your p-value, right? So your p-value gave us 0.02. 63, right? While your significance level, they told us, was 5%. So 5% as a decimal is 0.05. See? So clearly the p-value is less than significance level. And so if the p-value is less than significance level, what I'm observing is too unlikely. And if what I'm observing is too unlikely, it's too crazy, then you have to reject HO. Which actually, again, putting it in red, is the current scenario. But just so that you can complete your notes, technically the alternative is that if your p-value is greater than a significance level, then once again you fail to reject HO. See? So again, have very clear, when you compare the p-value with the significance level, you are talking about probabilities. When you compare the chi-squared with the critical value, you are comparing like a benchmark or something like that. Like if it goes beyond this number, it's way too big. See? The visual aspect, and this will be the last minute of my video probably, the visual aspect of this is the following. So a chi-squared looks a little bit like a normal distribution, just that it's very skewed. See? So it looks something like this. Boom. Okay? And so your chi-squared is here on the bottom. Let's say that the critical value they told us was 9.488. See? So this is 9.488. So this is my critical value. And essentially anything to the right of this is like a little too far out. Okay? It's not what you expect to observe. See? And one thing is that it's unlikely, another thing is that it's like crazy. See? So for example, values that are over here could be very unlikely to observe, but it's not too crazy. Well, anything to the right of the critical value is not only unlikely, but it's also crazy to observe. See? It's like a little too far out, and that means that my HO is probably wrong. That's the whole point of the chi-squared statistic. See? Now, that's my critical value. This is a little bit like your benchmark. See, like anything beyond this, you have to really question yourself what is going on. And the chi-squared that we figured out was 11. 11. This was my chi-squared. So clearly, it's to the right of the critical value. It's to the right of the benchmark. So it's a little too far out. The difference between your expected and your observed is a little too much. So that is how you would interpret this. See? That is in the sense of like you're comparing like benchmarks and stuff like that. If you want to think about comparing probabilities, well, probability with a curve has to do with the area under the curve. See? So for example, this right here could maybe be like the 5%. See? And you got like a 2% that's over there. See? So anything that's below 5%, that's 5% or below, it's the same as saying that you're from the blue line to the right. Just that you're thinking in terms of area. So this is the 2%, ¿cierto? Clearly it's within the top 5%. It's a little too far out. It's too unlikely. H0 is probably wrong. See? So that is how you evaluate a chi-squared. Here is the visual aspect. See? And honestly, instead of remembering all this, because I know it can be a hassle, I know it can be hard, you can just kind of memorize what I'm going to put now in green. See? So if you memorize this, and you memorize that, you're going to be good to go. See? It's not too much to memorize for getting easy 2 or 3 or 4 points. Okay? And remember, You're not gonna know by memory when to use which chi-squared, but remember that you have a list of tools, okay? Go one by one, discard them. You don't have to know all the tools by memory, but you do have to know roughly which ones you have. That's the main message I want to pass to you today. And yeah, I hope it helped. So that is for number 6.